by this, we go back to the technology of slab track, and again, it's interesting from an American perspective, at least for one reason, and that is we have very little use of it. In the United States, we have several kinds of ties, sleepers. We have conventional wood ties. There's a large number of installations now using concrete ties, and various other tie technologies are either used by particular railroads or experimented on. But we don't have we have hardly any use of slab track installation in the United States. So here in China, they pretty much abandoned ballasted track for their high-speed lines. And one quick word about the Chinese high-speed system. In the last, say, 12 years, China has gone to from having 0 high-speed services for its passenger railroads in service to somewhere around 9,000 miles. The Chinese high-speed installation is incredibly quick, incredibly fast. It is as if the planners were able to draw a line on a map, and magically that line turned into a high-speed rail installation with trains moving about within 24 months. China's advantages in installing its high-speed train system include very little process, and by process I mean the kinds of process of planning, design, environmental analyses, and approval that we are used to for all of our projects. And the other significant advantage is that political will to make an investment is quickly followed by the investment. There's very little political process around these kinds of decisions. And I guess the last advantage that China seems to have is what seems like an unlimited amount of capital to invest. China has decided that high-speed passenger railroading is the only way to knit its country together and change dramatically the sense of time and space between important places. So high-speed trains now are connecting the key activity centers of the country, and the program continues to deploy new high-speed lines. So ballastless track in China. Ballastless track has been used in the initial high-speed lines that have been installed between Beijing and Tianjin, Wuhan and Guangzhou, Zhengzhou, Xi'an, etc. They have more than 2,100 kilometers in those services of ballastless track. And another 2,500, here the slide says, will open soon, and soon has already happened. So this list includes 4,600 kilometers of ballastless track installation. The differences in climate and geological conditions need to be taken into account with ballastless track installation. It has also been used on bridge and tunnels, in bridge and tunnels, and it has become the standard track structure for the Chinese passenger railroad system. So we have a list of the ballastless track installations, and kind of a description of different climatological and geological structures in each of these. So the differences needed to be solved in terms of design, different climates and infrastructure. There needed to be compatibility between the ballastless track and the electrical circuits that control the service with its signal system, and power the trains and the signal system. They are focused completely on settlement and the under carrying capacity below the ballastless track, and so they have dealt with soft soil, collapsed soil being controlled. They are, very focused on installing ballastless track on top of very stable um, track structure below the slab. They're also dealing with the deformation of long-span bridges, again, taking into account the movement that's caused by heat and train loading with respect to how to lay the ballastless track. And lastly, with respect to the technical design criteria and application during construction, they have integrated survey, construction itself, and maintenance, so that there's one control network for these three engineering stages. So that they're looking for ballastless track technology at the design stage, designing the structure, interfacing that design with the rest of the infrastructure, including the catenary, and the technical requirements that will need to be faced during construction at the design stage. And then in the construction itself, making sure that the surveys are proper, that the technology of the materials is proven, and that the technology of manufacturing the slabs works and is integrated with the design criteria. And then lastly, that the technology of laying the track across the new railroad line is proper. And then lastly, once the service is in place, the inspection and evaluation of what is found in the inspection needs to be taken into account, the technology of repair and maintenance, and then in some cases being able to quickly respond to a problem in the track to maintain reliable service. So there's two types of ballastless track. One would be manufactured at another location and brought to the alignment and laid into the infrastructure, pre-cast, and then a second type which would have cast-in-place ballastless track slabs that are literally cast in place. And those two different ways of doing it really relate to the technology required by the place and by the geotechnical conditions and by the construction methodology and speed. So you have different construction types to reduce the influence of environment and weather on the final product. So here is precast. This picture shows you a precast installation. These slabs were manufactured and then delivered to the service. The in situ or cast in place is used when the tunnel sections are used or subgrade situations. So here, in a in place concrete creation of the slab track, they use longitudinal continuous concrete bed structure. It's used also on bridges, and they create an intermediate level, an intermediate layer to keep the concrete bed and the support foundation separate because of the movement of the structure. So strength and stability yields very high safety. The design scheme also takes into account the smoothness, the ride quality issues that need to be faced, and of course the last criteria here yields low maintenance costs. The better the design, the better the construction and installation methodology, the more dependable is the criteria of low maintenance. An interesting diagram that sort of describes all of the whole process of design and then installation and maintenance of ballastless track. Design requires the calculation of temperature stresses and the forces that are created by the range of temperatures that are predicted at the site. The warping stress, here's a formula that I will never use, and probably you will never either. An analysis of deformation on structures, again because of the unique train loading and the civil engineering aspects of the beams that carry structures. Classification of loads that takes place, the structural weight and the shrinkage and creep of concrete has to be taken into account, so that the design considers the braking and traction forces of the trains, the uneven settlement, and the live loads of the trains moving across, the temperature, the vertical, lateral, and flex of the bridges to define all the loads. There's a huge amount of loading analysis. And here's a diagram that shows the dynamic evaluation, looking at the train, the track, and the foundation dynamics, taking into account the loading requirements. So the whole this whole presentation really introduces a level of analytic detail that is needed to make the decisions for final design and construction, and then installation and maintenance of ballastless track, looking at safety, looking at comfort, looking at the dynamic response to the forces being applied. So the engineering structure, the flatness, the elevation, the vertical and horizontal curves, the design requirements for parts that are embedded in the system, and lastly, taking into account all of the drainage requirements to make sure that the structure is drained. And then there are other appurtenances put into the system with respect to the track circuits, the train control system, the ability to install devices in the system. All of this has to be taken into account. So here are 9 technical requirements and key technologies to be taken into account with respect to the fastening system itself. And I think it's important to understand how important the fastening system is to keep the gauge of the track, to maintain it, to resist rail climbing, to resist the reduction in performance, to make sure that installation of the electrical system is maintained, the ride quality, etc. So these are key technologies that have to be taken into account when the fastening system is installed and designed. And you can see again another picture of a fastening system. It's quite complex, it's quite elegant, and it does all of the things that those 9 criteria required. So here's, just in case you wanted to differentiate between a WJ7 and a WJ8, you have good illustrations. We will not be doing any testing as to the difference between 7 and 8. So here's a picture of the application of WJ7 on a slab, and here's another picture which shows WJ8 fastenings on slab track. So when there's a turnout, things are a bit different, and turnouts require different kinds of fastenings to maintain the movement of the turnout and its ability to move a train at very high speed. And at this point, we're talking about continuous welding rail on long spans, on turnouts, and using a CWR for long installations. And again, CWR is the standard for a high-speed rail, and perhaps today you could say continuous welded rail is a standard for most freight and passenger rail installations. So here's a CWR design. CWR is laid on the track, on the slab. In some cases, it's installed with as part of the slab when it's manufactured, and then all of the junctions are welded. Here's a turnout design for a non-ballasted track installation with a 56-meter beam bridge. So one of the things about high-speed trains is that the turnouts are designed to be very fast running with diverging and converging moves made very quickly. So here's a discussion about turnouts. So the standards have been set in China for high-speed lines for ballastless track. There's a design code, there are technical standards, there are operating rules, and quality acceptance criteria. And these are used